Hey guys, just wanted to add a couple things to these videos today. Sorry to do 4 videos, but you know how it goes. Just wanted to be clear about DNA replication, right? You should be able to draw a diagram like this. And I think we've done this on the board before, right? You have a DNA double helix, right? The double helix is untwisted, and then for DNA replication, it's going to unzip. These hydrogen bonds will break here, so I'm going to take this down and I'm going to just separate it out from themselves, right? So that's the double helix unzipped, and then new nucleotides are going to fill in, right? There's the first nucleotide. Here's the next one, according to base pairing rules, of course, right? And so in that way, the 2 new strands get built out like that, right? And this is basically the level you need to know it. But I just want to point out to you that each new strand has 50% new DNA, 50% old DNA. And if we do have one more generation of this, if we make this DNA replicate now, right, it'll look something like this. Right, there's the separated double helix. Here's the separated double helix. Right, I've just, again, separated those out. And then I fill in with new DNA. Boom, 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 boom. I'm making this a little sloppy, but you get the idea. Right? After 2 generations, 50% of the DNA has old DNA in it only. If I did this out again, it would be only 25%. I just want you to keep track of where that original DNA was so you can sort of think it through like this. Just a helpful diagram, I think, to just kind of wrap your head around certain aspects of DNA replication. Now, to show you with a mutation, I'm going to add letters to this. Right? I'm going to do basically the same thing I just did, but this time we'll make the DNA have labeled base pairs. So A with T. We'll do this C with G, and we'll make this a T and an A. All right, just 3 codons, or 3 letters rather, 3 base pairs. All right, so let's say I separate this out. So we've got A, C, T, T, G, A. And let's say that we're going to bring in the new letters. So the new one will be a T. We'll do a G here, and we'll do an A. So that molecule's done. This one, we're going to do a T. We're going to do a C, and we're going to do a T, right? No RNA we have to worry about here. So there's no U's. Now you'll say, wait a minute, Mr. Harris, didn't you make a mistake right here? And that's correct. I did. Sometimes mistakes occur. Now, T is a smaller base, so like the molecule would look right here. We have these proofreading proteins that can attach to the side of the double helix and kind of zip up the molecule, checking it. Now, when it gets to this, when these proofreading molecules get to this, they'll recognize this is incorrect, and they will fix it. But they'll only get this right about half the time. Let me show you why. I think we've done this in class. I have a vague memory of doing it. Half the time, the proteins will get to this point in the DNA and they'll say, hey, T with T is wrong. This is supposed to be an A. And they'll take out the T, they'll put an A, and the problem is fixed. Notice both of the new molecules now look like the parent. The other half the time, though, they will say, hey, this should be the A. And they'll change the wrong letter, right? And now we have a mutation that's fixed in here, okay? It might be more helpful, I'm just thinking it through for myself right now, if you saw it like this. If this was the T, you're supposed to put an A there. What if they put a G? Right? Oh, that's a mutation, that's a mistake. Right? So half the time they'll say, hey, that should not be a G, that should be an A. And the mutation is fixed. The other half the time, though, they'll see, oh, a GT pair is not right, this should be a C. And now, whoops, you've just put the mutation in there, right? And now this cell, after cell division, this cell will be fine. This cell will have a mutation. The last thing I wanted to show you real quick is the difference between frame shift and gene mutation, right? I'm going to write a sentence. The fat cat ate the rat. Can I fit this all in the camera? right? The fat cat ate the rat, right? Now, if I were to change one letter, do a substitution, right? Let's say I put an O instead of an A. Now the sentence says, the fought. Woo, oh no, my camera. Oh God. Seriously, remote learning sucks. I'm just kidding. The fought cat ate the rat. And so that would be kind of like a substitution. Oh my God, my tripod is not staying up. And what about a frame shift type of mutation? Right, so I'm gonna go back to the fat cat ate the rat. This time I'm gonna do a frame shift. I'm gonna do a deletion. I'm gonna take away this E. Right, now watch what happens. Vefa atka ata tet her at. Right? This is what happens with a frame shift mutation. When you add or remove a letter, especially one early in the gene, everything after it gets affected because everything shifts down one. This is how a frame shift mutation works. All right, that'll do it.